Hi, this is Jeff Heaton. Welcome to Applications of Deep Learning with Washington University. This is Module 4, Training a Neural Network. Part 1 is going to be about feature vector, encoding, and early stopping. You'll often hear of the feature vector referred to in many areas of machine learning, especially neural networks. The feature vector is just the input that is going into a neural network that you're going to form predictions on. We saw the iris and MPG data sets before. The four measurements about the iris, that's the feature vector for the irises. The various measures of the car, like cylinders, acceleration, and other things used to predict the horsepower, that's the feature vector for the miles per gallon data set. You will need to encode that feature vector often to improve the neural network's predictiveness. This is a very, very deep area of research, often called feature engineering, trying to create the best encoding of the data to go into the neural network. This is one of the areas that deep learning is particularly strong at, in that it can often engineer features and save you some of the time and trouble of trying to figure out the best encoding on your own. However, some degree of feature encoding will still very much help you. Later on, we'll learn about something called autoencoders, which is a way to have the neural network perhaps do some dimension reduction and feature encoding for you. So your data coming into a neural network from a data set, it needs to be completely numeric by the time that it goes into a neural network. And to make it numeric, some of the values are numeric already, like the four measurements for the iris flower set. Those are already numeric. There's other things you can do to them to process them further, but they're already essentially numeric. Other data sets, you may have things like colors, and in the case of the miles per gallon data set, the country of origin is actually, it's there as a number, but it really shouldn't be treated as numeric. So we'll see ways to encode that. As far as the data that you have in a data set, you have two high-level categories of data. You have character data, which is strings. This needs the most amount of processing before it goes into the neural network. You really can't feed strings directly into a neural network. Now later, when we get into the LSTM networks and natural language processing, we'll see that you can pretty much send strings in for certain situations if you wanted to read a sentence or something such as that. And then there's also numeric data. Numeric data is just data that's already a number, and the number makes sense. You need to think about, just because something is a number does not mean it's numeric data. For example, United States zip codes, 63017, for example, that's really not 63,027. You can't add or subtract two zip codes to each other. You can't multiply it. If two zip codes are close to each other, it probably means that those areas are close, but you really can't be sure. It's not necessarily defined in the encoding. As a result, you don't want to just encode a zip code into the data set. You might want to convert it to like a latitude and longitude, because then you have sort of a grid location of where that zip code might be. You might encode a zip code as the number of miles from a major city, something such as that. But the point is, don't just pass that numeric value of the zip code in. You need to do some sort of encoding on it. Of the character data, we have two different types. There is nominal and ordinal. If you're not totally sure what a string actually is, treat it as a nominal. That is something like the zip code, a shape, maybe a color. You simply can't find an ordering to it. Certain strings you might be able to order. For example, degrees, bachelor, master's, or even associate, bachelor's, master's, doctorate. That's four different levels. That's normally that's a character string. It would have that word in there like master's or doctorate. But there's an order to those. You could just assign 0 to no degree, 1 for associates, 2 for bachelors, 3 for masters, and then so on and so forth. So that is an ordering, and the order makes sense. That's an ordinal. So always try to order the character strings if you can find something. Like if you have the high school or undergraduate levels, freshman, sophomore, senior, junior, senior, you could assign those to numbers, and that way you don't have to encode those to dummy variables. And dummy variables are how we encode ordinals. So if you have something like the four levels, or the 3 regions that the cars are divided into, Europe, United States, and Asia, what you do is you actually create 3 columns, and only one of those values will be 1. The rest will be 0. This is also sometimes called one-hot encoding. So you simply, we'll see some examples of that as we go through, but that's how you normally encode those. The problem is, say you were doing zip codes, and there's quite a few of those. I don't know the exact number, but there's thousands, maybe 10,000. That would just be too many dummy variables, because you'd need a column for each of those, and then just one would be 1, the rest would be 0. So it's always try to find something else rather than doing the dummy variables. If you have to, go ahead and use the dummy variables, and we often do use them. We'll see many data sets where we do need to do this. Numeric data, there's 2 types. It doesn't matter so much unless you get into really advanced encoding, so both of these we'll just treat as numeric, but the 2 different types that you have are interval and ratio. Interval is something like a temperature. You would not say yesterday was twice as hot as today. That is just because there's no defined start. If you were dealing in Kelvin, you could. Ratio is where you have a defined start at 0 typically. You could say that the first car is going twice as fast as the second. 20 miles per hour is twice as fast as 10 miles per hour, but 20 degrees centigrade or Fahrenheit is not twice as hot as 10 degrees. I give you a variety of functions that you can use to encode these. They're always at the top of the class sections and or class modules, and you'll want to run those just to make sure they're in memory so that you have them. I'm going to just go through them briefly in this module, and then we'll look at them in much greater detail when we get into preprocessing. Encode text dummy, what that is going to do is it's going to encode it. It's going to encode a categorical or a nominal value into dummy variables. So if you had 3 classes, 3 different things that string could be, one would be encoded as 001, 010, 1001. So dummy variables, they're groups of columns. Only one can be 1. The others must all be 0. You will usually encode strings that are on the X side or that are fed into the inputs of the neural network as dummy variables. If you're trying to predict something, you will also potentially encode that as a dummy variable for Keras. The 2xy function somewhat does that for you, but the output neurons for categorical, for classification neural network, you have multiple neurons, one for each of the classes that's trying to predict. Encode text index, you'll do this in more special cases. Sometimes you'll do the target for classification this way. This is good for nominal. It would encode your classes as 0, 1, 2, so on and so forth. Encode numeric z-score. What this does is it takes any numeric value and encodes it as a z-score. A z-score just means 0 is the mean value. So if you see something encoded to a z-score, 0 is the mean. That means it's very average. +1 means it's 1 standard deviation above. -1 means it's 1 standard deviation below. That keeps very large columns from overwhelming very small ones. So if you had a column that was the price of a house, for example, which would be hundreds of thousands in US dollars, and another column that was the age, which would probably not exceed 120, that is something that you might want to encode both of those as z-scores. That way you don't necessarily have the very, very large home value overwhelming the relatively small age. Missing median is a very handy function. You can call that for a particular column, and any missing values, it will put in the median value for them. So it handles missing values that you might have. Hours, minutes, seconds string is a way of printing out the elapsed time. When we run very long-running neural networks, which we'll do in a couple of modules, we'll time them just so that we can see how fast one runs versus another. Chart regression, we'll see more about that in a future module, but it draws a lift chart, so you can start to evaluate how well a regression chart is doing. These are all of these functions in Python. We'll see more of these in the feature, or the preprocessing, but all of the classes will have these, and these are all exactly the same. We have not learned all of these yet, but the first time I taught this class, I had separate versions of this as it was slowly revealed through the semester, and that got to be too complicated. Students were using an earlier version when they should use a later, so they're all the same. You just need to run this, and then they are loaded into the Python memory for you. Okay. So we've already seen how to train. And what we did with training before is we just picked a number of iterations. Each iteration through a training loop of the neural network slowly drags those weights using various forms of gradient descent to values that are more and more and more optimal. We would always, before we just arbitrarily picked a number of iterations. The problem with that is if you pick too many iterations, the neural network keeps training and training and training, and it'll overfit. It'll start to memorize the training data rather than generalize it. If you don't run it for enough iterations, then it's going to start to, or it's not going to get those weights pulled to a truly optimal value. So there's almost just this pinnacle point of when training is the best. We'll learn how to evaluate in this module in a subsequent part, but what happens is as you train, your training error is how close your expected output from the neural network is to what it's actually doing. So how well the neural network is performing. The expected output and the actual output will get closer and closer and closer. And at some point, when they get really, really close, or even at some point, you don't know when the point is. That's the point. So you must know when to stop. How you stop is you take 80% of the data, you use that to train. Then you hide 20% from the neural network. It doesn't get to see it for training. And that's your validation set. So as you train, your training error, your error on the training data will go down, 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 down. Eventually, it'll very much flatten out and slowly start to really slowly converge to lower and lower. It's very rare that it would go completely to zero unless you have a trivial data set. But at some point, the validation set is going to the error that you're getting on the data that the neural network doesn't see, that it's not training on, it'll eventually track down with the learning rate. But at this point, right around here, is where you start to overfit. Because the neural network, it's going to keep training, but it's learned as much as it can. It really needs to stop at this point. Or you take other actions, but for now, we'll just stop it at this point. That is called early stopping. We'll still specify a real high number of iterations. It doesn't matter. You could say 1 million iterations. But at some point, you will tell it, okay, if it hasn't if it hasn't improved the validation for whatever your level of patience is, then stop, early stop. You really, from this point forward in the class, do not want to simply train without a validation set and some sort of early stopping. Otherwise, you're not going to know when to stop. Your training error rate's going to get lower and lower and lower. This is also called your in-sample error rate. This is your out-of-sample error rate. Because this is inside of the sample that you're training from. This is outside of the sample that you're training from. So always use some sort of a validation set. Otherwise, you just don't know how far to train your neural network and you'll risk overfitting. There are typically 3 sets that you'll hear of. Often we'll just do training and validation. But if you really want the ultimate in knowing how well your network is going to perform, and if you have good access to data, you can also use a holdout set. So what you do there is you keep a holdout set that is going to be the amount that so it's separate even from the training and validation. So before you even do this, your original data set, you take off maybe an additional chunk of it and you hold it till the very end. Because since you're early stopping on the validation, your neural network is a little bit aware of the validation because it stops once that improves. If you hold a set completely separate than the validation set, then you have the ultimate sort of test for that. Okay, so now let's see how to actually implement that in code. We're going to do that, do the 80-20 split. We're going to train on the training and then use the validation to evaluate it. The point is, this training part never saw the validation. We don't see it until the very end because the neural network quits learning when you stop training it. A neural network is not like a human, well, most of the types anyway. It's not constantly learning. Once you're done with training, it has learned what it's going to learn. So we're going to use the iris data set. We're going to read it from the data directory. This is exactly what we did before. We're going to encode the species as a text index. Like I said, you should use the text index. So that's going to take the species, the characters, the iris, setosa, versicolor, all the 3 different iris types, and change it into 0, 1, 2, numeric values. Then we're going to split it into x and y. X is going to be the 4 inputs that let you predict the species. Y is going to get actually increased to 3 dummy variables that correspond to that 0, 1, 2 that you've sent to it. This is a very important function here that we are using for the first time. This is how you do a train test split. And this is coming from scikit-learn. You are essentially taking your data, your x and y that you've created. You're saying that you want the test or the validation size to be 25%. So we're doing 25% instead of 80. It's usually somewhere in that range. And we're specifying a random state of 42. It is the Hitchhiker's Guide to the Galaxy. Number 42, the answer to everything. It's just a common number that is used as a seed in a lot of Python and other examples, so I just follow suit with that. 42 just means that you will get a consistent train and test split no matter how many times you run this. If you want a different split, move it to 43 or some other value. Then we're going to create our, so that's how we get that, and that puts it into 2 parts. You have an X train, an X test, and a Y train and a Y test. So that's your test and your train and your validation, they call it a test here, sets. Then we create our neural network just like before, sequential. Very simple neural network, 10 inputs. Actually, I'm going to do 10 and 5. I like that a little bit better. So 10 hiddens. The input neurons are going to be equal to the shape of X, which is going to be 4 in this case. 5 hidden neurons, and then an activation function of the rectified linear unit. We almost always use the rectified linear unit for hidden layers in this in this course, except we do use softmax always on the output of a classification. You simply don't specify one and use linear for regression. Since this is a classification problem, we'll use categorical cross-entropy. Softmax categorical cross-entropy, that's how you know that it is a classification problem. But now we're doing something different than last time. We're creating early stopping. Early stopping, and we just give it a name, validation loss. You can name it anything you want to, really. This is the minimum amount of time, or the minimum amount of change, so 10 to the negative 3 size that you're allowed to improve for it to be considered an improvement. And patience 5, that means we have to improve for 5 or more times, otherwise it's going to stop. It's going to early stop. And verbose just means that it's going to give us some information about that. We're going to fit to the x and y just like before, except now we provide validation data, so x test, y test, and we provide a callback. And we're also going to produce verbose output here, and we're going to do epochs to 1,000. It won't make it that far. It'll early stop. So if we run this, we can see that happen. And here you can see the output from this. It went quite a ways. You can see the validation loss consistently decreasing, though, on the right side. And then it stops, early stop, on epoch 311. So then it's going to go back and find the weights for the lowest validation stop, or the lowest validation loss that it had. And that is the neural network that you now have. And we can print out the initial predictions. Again, these are probabilities. This would be the one that it's predicting for the first one. So that would be 0.996 given scientific notation. So it's very sure that it's that one. We'll see that we'll be able to calculate the accuracy and other statistics on these to show how good of a fit the neural network has in the next part.